at some point C, or as x approaches C equals L, if and only this is if what? If this is if part. This is only if part, only if this part. I think this is obvious. Let's consider a picture here. Suppose the function, this is position C. Maybe f is defined or undefined at C. Okay, maybe this is a linear. This is perhaps the plot of the parabola. And f is defined at C. The value of f at C is here, not here. Not here. Okay, in this case, obviously, the limit of f at C, or the limit of f of x as x approaches C, is L. See, if we consider some neighborhood of C, then the values of f of this neighborhood from here to here. Yes, when we talk about a limit, we never consider the number, the point C. Never. So this is exactly, this statement is true. Of course, here, if we consider a neighborhood of C, maybe not large, small neighborhood, only consider the right-hand side, the right part of the number C, on the right of C. Also, if this is small, and small, we have this statement. If we consider the left-hand side of this position, then we have this one and this one. If this interval is considered smaller and smaller, this is true. Conversely, if this relation is true and this relation holds, then put together, this part and this part together, we have a complete neighborhood of this point. So sometimes this theorem can give us some advantage to prove whether this limit is L or not. Suppose in this case, the right-hand side limit at C is L. The left-hand side limit of L at C is M, and L and M are different, are distinct. Then we conclude this limit does not exist. No limit for this function at number C. According to this theorem, in this case, for this case, the limit of the function f as x approaches C does not exist. Okay, suppose it exists, must be some number, for example, L. Then we must have, this is L and this is L. But we already given this condition. They are different. So this limit does not exist. Okay. Mathematics must be very reasonable. If you realize the key point, yes, not hard to realize, not hard to realize. Okay, so this is the limit, the notion of limit, one-sided limit or two-sided limit. The limit gives us the capability to deal with function undefined at some position, but defined nearby that position. The behavior of this function sometimes completely determine the behavior of the function on the neighborhood of that given point. Of course, when we talk about limit, that specific position we never concern. Good. Then, if C is far, far away from the origin, if the number C is far, far away from the origin, for example, here, again, xy plane. Just now, we consider C here, a finite position here. Suppose C is far, 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 far away from the origin. We may consider limit not at C, limit at infinity. At infinity, not at a finite position. Okay, suppose we have a function that looks like this. Or y equals f of x. And this function is defined maybe again, for large enough x, quite similar to a neighborhood of C. But now C is at infinity, so for x large enough, or some interval, oh yes, this is also an interval. Suppose f is defined for large x, and for example, greater than or equal to greater than 8, for example. In this case, suppose the position here is L, then we give this event a notation, limit of the function fx as x approaches infinity or plus infinity equals L. So we generalize C from a finite number to an infinite number. Sorry, not number. Just give this phenomenon a notation. We just give this phenomenon a notation. Similarly, we can consider limit at minus infinity. Okay. Now, the graph of the function f looks like this. A curve on the Euclidean plane. Okay, when x, this function defined when x small enough. Small means the left-hand side of the origin, or from some place that all defined. In this case, we may consider the behavior of f when x is very small, and use this notation. Here we know if to the left, to the left, to the left. So this value is L. Okay, we may consider this concept. Limit at infinity. Usually, limit at infinity, if it exists, this L is a finite number, then some geometric intuitively, there must be a horizontal line, this one, such that the curve close to this line arbitrarily as x is very large. Okay? So if this one is hold or this one is hold, then we say y equals L is a horizontal asymptote of the curve or of the function f. Okay, horizontal asymptote 水平间际线 if limits at infinity exist, if limits or a limit at infinity exists, then we say this y equals this one is a horizontal asymptote of the graph. Y equals x. Yes, very good. So definition make things easier. Make things easier. When we say y equals L is a horizontal asymptote of the function, automatically means this holds or this holds. Okay. Automatically you can imagine the behavior of the function looks like this or looks like this. If we have some definition, use some terminology, then when we talk about this now, proper noun, everyone knows what you say. We have the same recognition. Okay, this is limit at infinity. Sometimes the behavior of a function looks like this. Okay, in this case, a finite place, finite position. So we can talk about x approaches c, the limit of the function f of x. But here, if x goes to c, we consider some neighborhood of c. You realize, oh, so maybe we have better to consider s approaches C from the right, we consider one-sided limit first. So C, we don't care. The value of C, whether f is defined as C or not, we just consider the values of f nearby C and greater than C. Oh, here, if we consider smaller neighborhood of C, this interval shrunk, smaller and smaller, and then go get far away from the origin, to the sky, up to the sky. So this limit does not exist, but we still can get this phenomenon in notation. In this case, we have so-called infinite limit. This is an infinite limit. So different from this. This is limits at infinite. But here, infinite is an adjective. Modify this limit is large and large, as large as you want. Okay, this is called the infinite limit. Similarly, we may have this four kinds of infinite limit.